Morning, guys. Today we're going to continue our study of waves by looking at sound. So today we're going to look at the difference between sound volume and sound intensity. Believe it or not, those are different things, and we'll see the difference today. And to really understand what's going on with that, we need to briefly talk about logarithmic scales. That's not as scary as it sounds. I know that's a weird word, but there it is. And then we'll move from that to decibels, which is probably something you already recognize as a way we measure how loud sounds are. And then if we have time in the 15 minutes, I may talk a little bit about the video you watched about the tsunami in Japan. Okay, so let's start off here first with sound volume versus sound intensity. Okay, now these are vocab words, and as you know in your homework today, you're going to be defining a whole bunch of words. That's to get you ready for tomorrow's topic in the lab that we're going to do a little bit later. But some of those vocab words are sound loudness versus intensity. So the implication here is that they are different. Okay, here's the short version. Sound loudness is a description of how loud it sounds to you. In other words, this is your perception of differences between two sounds. It's perception. Now, sound intensity is a measure of the amount of energy that is carried by the sound wave. So this is objective reality of how much energy actually is impinging on your eardrums when you experience a sound. So the difference between loudness and intensity is your perception versus the reality. Okay, your perception is subjective and it depends on the environment and conditions before you change the volume on the radio. It depends on a lot of things which make it kind of squishy. So loudness is not a precise measurement of a sound. Sound intensity, which is a direct measurement of the energy carried by the wave, that is measurable. We can set up instruments that can record this, and we can compare sound. We can hang a number on it of how much energy is actually impinging on your eardrums, how much bones in your ear are being rattled. So loudness versus intensity is the difference between perception and reality. Now, before we can get into why it's important to distinguish between these two, I guess the preview is that the way we perceive sound and differences in sounds, how loud one sound is compared to another, is actually not related to how much energy those sounds carry. And that's why we have to distinguish between them. Okay, so now we have to look at a decibel scale here. Okay, so decibel scale. Now, a decibel scale is a logarithmic scale, and I said I would explain what a logarithmic scale is first. So let's do that. Okay, a logarithmic scale is different than a linear scale. And a linear scale is what you usually deal with when you're making graphs or doing math problems or whatever. So a linear scale, like is on a meter stick, and the distance between 0 and 10 centimeters is only half of the distance between 0 and 20 centimeters. So if this was a meter stick, which it's not, but just pretend for a moment that it is, the distance between the 20 centimeter mark and the 30 centimeter mark, well, that's 10 centimeters. And that's half as far as from 20 centimeters to 40 centimeters. If it's a linear scale, this interval represents the same difference as this interval, which is the same difference as this interval, and so on. Every interval is the same. Now, in a logarithmic scale, that's not true. In a logarithmic scale, this measurement is 10 times as much as this one. So 30 decibels is 10 times as much energy as 20 decibels. And 40 decibels is 10 times as much energy as 30 decibels. 50 decibels is 10 times as much energy as 40 decibels. And what this means is that they multiply. So we might look at it and say, hey, 40 decibels is 20 times as much energy as 20. And no, it's not. It's 100 times as much, because each time we're multiplying by 10. We start off with some amount of energy here at 20 decibels. And when we go to 30 decibels, we have 10 times as much energy. Say we have 5 joules of sound energy at 20 decibels. It's nowhere near that much, but just work with me. Say we had 5 joules of energy here. 30 decibels would be 50 joules of energy, 10 times as much. And 40 decibels would be 10 times as much as 30 decibels. So if this was 50 joules, this would be 500 joules. And the next one would be 5,000 joules. We multiply the previous one by 10 by each interval in the scale. That's what a logarithmic scale is. It's a geometric scale where numbers expand geometrically rather than in a linear scale. If you graph it, it comes out to be a curve curving up rather than a smooth slope. Now, the way it's set up is this is true for all the numbers in the scale. So 35 decibels would be 10 times as much energy as 25 decibels. And 49 decibels would be 10 times as much energy as 39 decibels. So any 10 decibel change in the scale is 10 times as much energy. Okay, so that's grand. How do we perceive it? Well, we perceive it, and this is just a quirk of our own perception. A 10 decibel difference we perceive as about twice as loud. So a song comes on the your earbuds that you particularly like, and you want to drown out the conversation in the room, so you may turn up your volume so it's twice as loud, so it sounds twice as loud to you. You'd be going from like 40 decibels to 50 decibels, making it twice as loud. But in reality, you're getting 10 times as much energy impinging on your eardrum. Okay, now this is something that I want you to understand. Let's sum this up here. Sound volume is a matter of perception. That's how you perceive the differences in sound. Sound intensity is the reality of how much energy is actually entering your ears. Sound intensity in a decibel scale multiplies. So going from 20 decibels to 30 decibels is 10 times as much sound, but going from 20 to 40 decibels would be 100 times as much sound, 10 times 10. In contrast, your perception of the loudness of sounds when you go from 20 to 30 decibels is twice as loud. And if you went from 20 to 40 decibels, you perceive that as being 4 times as loud. Okay. Now, we have a tendency when we turn up the volume on a football game, when we're watching TV or a song on the radio, we usually do it more than twice as loud. We usually do it much more than this. Now, why does this matter to us? And I'll come back and I'll review that in just a moment here. I'll give you a chance to apply that. But okay, the reason that this is relevant to us is because of the way our ears work. Okay, now you have heard from your bio class, I hope, maybe you've had anatomy, maybe you haven't, but there's a part of your inner ear called the cochlea, which is looks like a snail. It's a curled up tube that looks like a snail, but if we were to unroll that and make it, it would look like this long cone. And this is the actual organ of perception for sound. It's where sound energy, vibrations in the liquid in your ear, are transformed into nerve impulses that go to your brain. Okay, and the way it works is this tube is lined with microscopic hairs. They're called cilia. And the fluid in the cochlea actually gets set up as a standing wave. The sound waves that enter from the eardrum, which is out at this end, sets up vibrations within the fluid in the cochlea, and it makes a standing wave, just like the standing waves we saw in before the break. Those water waves in the trough of water are standing waves on a rope. You get standing waves in the fluid in your inner ear. And as you know, in a standing wave, there's some places, the nodes, where the fluid is not moving at all, and there are other places, the antinodes, where it's moving a whole bunch. So you have a band of no motion and a band of a whole bunch of motion, and then a band of no motion, and then a band of lots of motion. And you have cilia all along here, and then nerves attached to those little hairs. And your brain kind of sorts out which hairs are being shaken by the antinodes, which ones are not being shaken because they're where the nodes are. And the brain recognizes those patterns and perceives the sets of hairs vibrating as different tones. Now, if you increase the intensity of the sound, you make the hairs move a lot more. And if you put in 10 times the sound or 100 times the sound or 100,000 times the energy in a sound, the antinodes shake so much that it will break the hairs off. And when those hairs get broken off, you now are incapable of hearing those sounds. That's hearing loss. That's why old people don't hear as well as young people, because we've experienced loud sounds and some of the hairs inside our cochleas have broken off, and we are incapable of hearing those sounds anymore. Now, if they're just snapped, if they're just fractured a little bit, they may repair themselves. They may grow back. And when they do, and when they come back online again and say, okay, when they hook up to the nerve and start to function again, we often will hear that as a very pure tone, a tinnitus or tinnitus, as people say, but a tinnitus, where you suddenly hear a very pure beep that just comes out of nowhere. That's your ear repairing itself from previous damage from loud sounds. Okay. So what's the point of all this? Well, I want you to understand the decibel scale. It is very revealing for the incredible range of energies that we are capable of perceiving. We can perceive very, very soft sounds around 30 decibels or so. That's about the softest sounds that we can hear. 20 decibels under perfect conditions. And we can also hear 100 decibels, which is like a million times, 10 million times as much energy. And our ears can both tolerate that difference in energy for small periods of time and perceive it, which is truly amazing, the range of energy that we can perceive. Okay, so let's review this briefly. How many times more energy is there in a 30 decibel sound compared to a 50 decibel sound? So 30 decibels versus 50 decibels. How much more energy? How many times more energy is there in the 50 than the 30? Okay, think about that for a moment. Remember, each interval is 10 times as much energy. So there's 10 times as much energy in 40 versus 30, and then 10 times again between 50 and 40, which means that there is 100 times as much sound, as much energy in a 50 decibel sound versus a 30 decibel sound. Now, I would like you to do an experiment at home, okay? I want you to take your two earbuds. A lot of you are listening to this through earbuds. You know there's the same amount of energy coming out of each earbud, so both ears can hear it. Now, if you take those two earbuds and you put them together, hold them right next to each other, and hold them next to one ear, put them both in one ear, you know there's now twice as much energy coming into that ear as there is when there's just one earbud. But if you do this, you'll find that the sound does not sound twice as loud, even though there's twice as much energy. Okay, it only sounds a little tiny bit louder. You can tell it is louder, but it's not twice as loud. To make it sound twice as loud, you'd have to get four of your friends and put 10 earbuds together and hold them all against your ear. And 10 earbuds at the same volume would sound twice as loud to you. Okay, so when you turn up the volume on your smartphone or on your Chromebook, when you turn it up so it sounds twice as loud, the speakers are actually emitting 10 times as much energy. Okay, so that's the difference between sound volume and intensity. Let's see. Now, how are we doing? I'm going to stop it right there, and we'll see if we have time for more. I think not.